Welcome, my friends. I'm so excited because in this video we get to talk about linear regression. That is, how to create the line of best fit for a scatter plot. This line will also help us to make predictions for our y variable based on our x variable. Now, unlike some statistics classes, we are not going to be doing all the by hand work to create this equation. Instead, we're going to be utilizing the TI-84 calculator. So let's go ahead and get started. Now, linear regression is tied very closely to the scatter plot. Specifically, linear regression is the process of trying to find the line of best fit for the dots on a scatter plot. But what exactly do we mean by the line of best fit? Well, what we mean is we are trying to minimize the vertical distance from each dot to the line on the scatter plot. Well, if you want to get technical, we are actually minimizing the squared distance from each dot to the line. What I mean by that is if we find the distance from each dot to the line and we square it, this is the line of best fit if that distance has been minimized. So let me just kind of give you some intuition by looking at a couple of the numbers here and kind of how this would work. So if we were trying to minimize the squared distance from each dot to the line, what do we actually mean by the squared distance? Well, look at this line where it kind of relates to this very first dot. If we look at the line, it is at around, I don't know, maybe about 20 or maybe very slightly above 20. So I can go ahead and I can grab my calculator, enlarge this a little bit here. And what I could do is I could take that value of 20 and then I could subtract where the dot is. And the dot here, let's just say that the dot is at about 28. So I'm going to subtract 28. So if I do that, I'm going to get -8. And then what I'm going to do is I'm going to square that value. So I'm going to multiply it by itself. So if I square that value, I'm actually going to get 64. And then I would do the same thing for the next dot. The next dot looks like it's at, I don't know, maybe about 15. And the line related to that is at about, I don't know, maybe about 23. So I'm going to take 23 and I'm going to subtract 15 and I'm going to get, well, 8 again. And then I'm going to square that value and I'm going to get 64 again. And I would continue to do this for every single dot and line kind of a distance, right? And if this is the line of best fit, when I add up all those numbers, when I add up 64 and 64 and whatever all the other values are, if this is the line of best fit, then that number should be as small as it possibly can be. So that's what we mean when we say we are creating the line of best fit. It is the line that minimizes the squared distance from each point to the line. And this is what we call sometimes the least squares line. So here's kind of the definition of linear regression. It is the process of finding the least squares line with the smallest squared distance from each point to the line on the scatter plot. Now you may know from algebra class that lines have equations, and we use a slightly maybe different form of the equation of a line than you might be used to. So you might be used to the form y equals mx plus b, but we're going to use a slightly modified version of that equation for linear regression. So the equation is going to be y hat is equal to a plus bx. And here's what each of those different values are going to represent. Y hat is going to be the predicted value for y. You might ask, why don't we just say it's going to be y? Why don't we just say y equals a plus bx? Well, if we thought about what y is actually going to be represented by the vertical distance or the vertical, I guess, position of each of the dots on your scatter plot. For example, the y value for this dot would be like 28, and the y value for this dot would be 15, right? And if you look at the line does not actually find the dots exactly, right? The line just kind of goes through the dots. So it wouldn't be appropriate to call this y equals a plus bx because this is the equation of the line. And the line doesn't actually go through each of the dots. So instead of calling it y, we actually call it y hat. So y hat is the predicted value for each of the y values. And then a is our y-intercept. A is basically where the line is going to intercept the y-axis. So once again, let me go back here. Our y-intercept in this picture is looking like maybe about 18 or so, right? Is where this line is intersecting the y-axis. B is what we call the slope, which is kind of determining how steep the line is. And then x is going to be our explanatory variable or independent variable that we're going to use to predict y. So the process of linear regression is going to be finding values for a and b to create the equation of this line so that it best fits the dots on a scatter plot. Now, there are formulas that can be used to find the equation of this line, but believe me, you probably don't want to do them. And since the purpose of this class is really more applied statistics and not really all the mathematics, we're going to be skipping out on the formulas and we're going to be using the TI-84 calculator instead. So here's an example of a dataset that you might use for linear regression. Note that for linear regression, both your x and y variables should be quantitative. So here we have the x variable, which is the number of hours that someone has studied, and we have the y variable, which is that student's exam grade out of 100 points. And we have created a scatter plot based on the x and y variables. So our goal with linear regression is to find the equation of the line that fits the dots the best. And once again, when we say the line that fits the dots the best, we really mean the line that minimizes the squared distance from each dot to the line. All right, to do this, we're going to be utilizing the TI-84 calculator. And the first time that you do regression on your TI-84 calculator, you're going to want to toggle a setting. So I'm going to show you how to get to that setting right now. So to toggle the setting, we're going to press the second key right here. And then we're going to press the 0 key so that we have entered the catalog. If you click on the x to the negative first power key, you will have scrolled all the way down to the d's. Then you can scroll down and eventually you'll see an option that says diagnostic on. Once your cursor is hovered over that one, we can press enter and then enter one more time and your calculator will say done. You should only need to do that step one time per calculator. So as long as you're using the same calculator in the future, you should never need to do this step again. At this point, we can enter into the stat list. So the stat list is a place in the calculator that allows you to enter data. And you can get there by pressing the stat key right next to the left arrow. So if we press stat, we will have a menu here which has a lot of different options. The very first option is edit, so I'm going to press enter so that I am in the edit menu. At this point, we can enter in the data as it relates to our scatter plot kind of information. So I'm going to kind of move this to the right-hand side here so we can kind of see both on the same screen. And if you already have numbers in here in your lists, you're going to want to clear those out. So to clear out a list, you can hover over that list. So if you arrow up to that list, you can press the clear key and then the down arrow, and that will clear out any of the numbers that are already in that list. Note that if you are hovering over a list and you press delete, you will actually have deleted the list. So make sure you do not press delete. Let me show you what happens if you press delete. If I press delete, that entire list 1 is going to be gone. So you don't want to do that. If you delete the list on accident, you can always go back and press stat and run the setup editor option 5. Press enter, and then you will have that list back. So let me get back into the stat list. Let me finish clearing out list 2. And I don't really need to clear out my list 3 because I'm only going to be using the first 2 lists for this data here. So now at this point, I'm going to go and I'm going to enter in all of those numbers. I encourage you to also enter these numbers in if you are following along. All right, so once you have all those numbers typed into your calculator, then we can run regression. So to run regression, we can press stat one more time. We can arrow once over to the right so that we are on the calculate menu. And then there are a couple of different options for linear regression. Note that you will see option 4, which is linreg ax plus b. That is not the one that we want. So if we go down a little bit further, we will see one that is linreg a plus bx. And if we choose that option, it's going to match the same way that I've given the equation earlier in the PowerPoint. So make sure if you're in my class that you're always using option 8. They really will give you the same information, but it's just going to switch around your A's and B's. So to not get confused, we're going to use option 8 every time. In here, you're going to want to make sure that your X list is list 1 and your Y list is list 2. So to change the list, if it doesn't have the correct one in there already, you can press second and then the number of the list that you want. So I'm going to press second and 1, and that's going to have changed my X list to L1. I don't need to change my Y list, but if I didn't have L2 in there, I could press second and 2 to get list 2. You should not need to change anything else in your calculator. The frequency list you can just leave blank, as well as the store reg EQ. You can go right down to calculate and press enter, and you should get all the information that you need. Now, if you are not seeing R squared and R at this point, that means you have not run the diagnostic on your calculator, and you should go back like 2 minutes in the video and see how I ran that setting. All right, so from here, let's go back to the PowerPoint. We'll talk about what that output means. Here is kind of the information here. So if you have access to my PowerPoints, you can kind of read it here if you are kind of doing this on your own at some future date. But basically, I have pasted that same information that I got from the calculator here into the slide. So now let's talk about what some of these numbers mean. So remember that our x variable in this example was the number of hours that were studied, and the y variable was the exam score out of 100. So from here, we can get the equation of the line. Remember, the equation of the line is y hat equals a plus bx. Now, I know that the equation in the calculator does not have the hat over the y, but they are lying to you. It really should be y hat. I don't know why they don't have the hat on the y. Every stats textbook anywhere is always going to use y hat for this thing, so it really should be y hat. So our regression equation here, if I rounded a couple of the numbers, would be a, which is 61.73, plus our b value, which is 3.0527 times x. And this would be our regression equation. So in other words, if we were to graph this equation on the scatter plot from earlier, it would be the line of best fit. Now you'll notice that the calculator does give us a couple of other numbers. It gives us r and r squared. So we're going to talk about those right now. We have talked about the correlation coefficient in a previous video, which is a measurement of how strong the line is going to fit the dots on the scatter plot. The general way that you should interpret the correlation coefficient, which just means describe the correlation coefficient, is that there is a either weak, moderate, or strong, either positive or negative correlation between your x variable and your y variable. Anything that's in brackets under the kind of bold parts here is something that you should replace with either one of the options, or in the case of x or y variable, you should replace that with whatever your x or y variable are. Make sure you are always writing these in the context of your given problem. So you'll never leave this as just x variable. You'll always replace that with whatever your x variable is, and same with the y variable. So in our specific case, we had an r value of about 0.7749. And if you remember back to the previous video, this kind of falls into the moderate / strong type correlation, right? So you could maybe say either moderate or strong. In this case, I chose the word moderate. We're kind of in the moderate range. There is a moderate and then positive, since this number is positive, there's a moderate positive correlation between our x variable, which is our studied, and our y variable, which is exam score. So anytime that I ask you to interpret the correlation coefficient, you should be coming back to this template here and kind of choosing the correct words based on your specific situation. We can also interpret the coefficient of determination, which is represented by that r squared value. Now note, the coefficient of determination literally is r squared. So if you take this r value and you multiply it by itself, you are going to get the r squared value. So in this case, that would get you 0.6605. The interpretation of r squared is a little bit more difficult to understand, but it's going to be in this general format here. It says that r squared percent, you're always going to put it in a percentage, of the variation in our y variable can be explained by our x variable. So let me take a second to try to explain what this means. So first of all, we're going to express this as a percent. So instead of putting 0.6005, we would say like 60.05%. And that is the variation in our y variable that can be explained by our x variable. So let me kind of go back to our data really quick. So if we look at our y variable, we can see that there is variation among those numbers, meaning that all those numbers are not the same, right? There's some difference in these numbers. Well, what explains the reason for these numbers changing? Why are these numbers not all the same? Why do these numbers vary? Well, we can say, based on this specific problem, that 60.05% of the variation in those exam scores, the y variable, can be explained by hours studied. And that means there are maybe some other variables out there that could explain the other 40%, right? But we can basically get 60% of the way to explaining the reason why those exam scores are varying just by the number of hours studied. Now, there's one more value that you might want to describe or interpret, and that is going to be the slope, which is represented by b. So in our case, the slope ended up being 3.0527 or so. And the general way that you're going to want to interpret a slope in this class is that for a 1 unit increase in your x variable, the y variable is predicted to either increase or decrease by the positive version or absolute value of the slope. So what this means is, every time you were to increase your x variable by 1, which in this case is the number of hours studied, well, that's going to add another 3.0527 to your prediction. So basically, every time you increase x by 1, the prediction for y is going to increase by whatever the slope is. Now, if you ended up having a negative slope, then you would end up using the word decrease. And I've got the kind of absolute values around here just to say that, well, you should always kind of use the positive version of the slope in this kind of last little part here, because either the word increase or decrease is kind of doing the work of positive or negative. Now, in this specific example, our x variable is hours of studying. So 1 unit increase in x would be represented by 1 additional hour of studying. So we would say for 1 additional hour of studying, the y variable, which is exam score out of 100 for a student, is predicted to, in this case, increase, since we have a positive slope, increase by that slope value, which is 3.0527 points. Well, what if this equation had been the same thing except for we had a negative value on the slope? What would that look like? Well, then we would still have the exact same first part here. So we would still have 1 additional hour of studying, and we would still have the exam score of a student is predicted to, but the difference here is instead of having the word increase, we would have decrease, since we have a negative value, but we would still write the positive version of the slope. That's kind of what this absolute value is telling us here. We should always write the positive version of the slope. So altogether, we would have for 1 additional hour of studying, the exam score of a student is predicted to decrease by 3.0527 points. So probably not all that realistic, based on this situation. Probably if you're studying more, you're probably going to get better. But I just wanted to show you an example of how you would deal with this if you had a negative slope. Additionally, we can use this equation to make predictions for y. So let's say we would like to predict the score of a student who studied for 10 hours. Well, hours is a value for x. So basically all we need to do is plug in 10 for x into our equation. We will get 61.73 plus 3.0527 multiplied by 10, which is equal to 92.257 if you plug that into your calculator. What this means is if someone was to study for 10 hours, then we would predict that their score on the test would be about a 92.257. What about a student who was to study for 40 hours? So maybe someone says, I want to get as good of a score as I possibly can on this test, and I'm just going to go and I'm going to study for 40 hours for this test. So what would this model predict that that student's score would be? Well, let's plug in 40 into the equation. We'll get 61.73 plus 3.0527 times 40, and if you multiply all that out and add the things together, you're going to get 183.838. So this would say if someone was to study for 40 hours, we would predict that their exam score out of 100 would be 183.838. So obviously that doesn't make any sense, and this is obviously a horrible prediction. So this doesn't really make any sense at all. So what went wrong is the question. Well, really, to kind of understand why we didn't get a very good prediction in this case, we need to talk about the difference between interpolation and extrapolation. So by interpolation, what we mean is we are making predictions for our y variable using a value for our x variable that is within the range of our initial data set. So what I mean by that is if we are plugging in a value for x that is anywhere from 0 to 12, we would consider that to be interpolation. Predictions made with interpolation are likely going to be accurate as long as we have a pretty good correlation, maybe something close to 1 or -1. On the other hand, if we are making predictions for y using values for x that are not within the range of our initial data set, such as anything that is bigger than 12, or in our example, 40, then we're going to be extrapolating, right? So then the predictions found using that type of method might be inaccurate even if we have a strong correlation. Now, of course, everyone, sometimes will ask me, what if we plug in 13? So I guess if you're plugging in 13, then are we extrapolating? Well, then technically, yes, we are outside of the range of the initial x's. But is there a problem with plugging in 13? Well, probably not. It really becomes more of an issue when you get far away from the kind of range of your initial data set. Okay, so interpolation is plugging in anything within the range that you kind of use to build the model. So basically anything from 0 to 12. Usually those predictions are going to be okay as long as you have a good correlation. Extrapolation, on the other hand, especially if it's very outside of the range of your initial values, is going to be inaccurate even if your correlation is strong, or might be inaccurate. Now, if you wanted to, you could go back to the scatter plot and you could plot that line of best fit onto the scatter plot. So here I've plotted that here. I have the point 0, 61.73. That's our y-intercept based on this value in our equation. So that's going to be one of the points on our line. And then you could just plug in any other point into the equation to find another one. Looks like I plugged in 5. If you plug in 5, looks like you get something maybe close to like 75 or so. And that would be a second point on your line. And then you can connect the dots. And that will be your line of best fit for the scatter plot. Okay. The last thing to talk about is the residual. The residual is the difference between the actual y value and the predicted y value. So the way you should think about the residual is if you're able to check your prediction and see how much you're off by, that is what we call the residual. So here I have the initial data set, the first two columns here, the hours studied and exam grade, as well as the prediction based on our equation and the residual. So with the prediction column, all I've done is I've taken each hour studied and I've plugged that into the equation. So if I plug 0 into the equation, I would get a prediction of 61.73. Or if I plug, for example, 6 into the equation, it looks like I get a prediction of 80.05. Now the residual can be found by taking each exam grade that we had and subtracting the prediction. So for example, 57 minus 61.73 gives us a residual of negative 4.73. Or 63 minus 61.73 for the second value is going to give us 1.27. And you can view each of these residuals as how far off the prediction was. So for the very first person, the prediction was 61.73, which was 4.73 off of the actual value, etc. for all the other numbers. Now, make sure that you're always doing the residual in this way. You are taking the actual value, y, and subtracting the predicted value, which is y hat. And if you do it that way, then any of the positive residuals are going to represent under predictions, and any of the negative residuals are going to represent over predictions, which might be a little bit backwards from what you'd expect in your brain. So let me just look at a couple of examples of those. So for example, this value right here, 13.21, is a positive residual. So according to this little rule here, it's telling us that that should be an under prediction. And we can see that is the case because the prediction was 64.78 when the actual exam grade was 78. So that's an under by 13.21. Or any of the negatives should be over prediction. So right here, we have a negative 21.84. The prediction was 67.84, but the actual grade was 46. So in this case, we have actually over predicted the exam score. Sometimes it could be nice to visualize the residual on the scatter plot. So here we have a scatter plot that is kind of using the midterm grade of someone to predict the final grade. And remember that y hat is going to represent the line, which is our prediction, and y is the actual point. And the residual is going to be the distance from the point to the line, or y minus y hat. So here we see the actual observed value, the actual final exam grade for one of the students was 59, but the model actually predicted that they were going to get a 70.2. So the difference between those two numbers is negative 11.2, representing that this person, they were over-predicted based on this model, right? This model predicted they were going to score a 70.2, but they only scored a 59. So here is one for you to try. So let's say that X represents the high temperature in degrees Fahrenheit, and Y represents the number of coffees sold at a cafe in a day. Let's suppose that the regression equation is y hat equals 45.313 minus 0.569 times X. So basically, if you want to predict the number of coffees sold in a day at this cafe, you would take 45.313 and you would subtract 0.569 multiplied by the temperature in degrees Fahrenheit. So here are a couple of things for you to try out. See if you can interpret the slope. So go back a couple of slides and find that general interpretation of the slope, or go back a little bit in the video, find that general interpretation and see if you can modify that to match kind of this situation. Secondly, see if you can predict the number of coffees sold in a day when the high temperature is 37 degrees Fahrenheit. Basically, that's just going to amount to plugging 37 into the equation. And then finally, if the actual number of coffees sold on this date is 27, find and interpret the residual. And if you're one of my students, this will be the one that you need to plug into you'll have to submit this answer. So I'll give you a minute to try that out, and then we will go over the answers. All right, hopefully you're giving that a try. So here I have the general interpretation of the slope that we talked about earlier in a handout that I typically give my students. So it says that for a 1 unit increase in X, our Y variable is predicted to either increase or decrease by the positive version of the slope. So we can kind of see how that might apply to this one. Let's see if I can kind of get it on the bottom here. And you can see my answer and how that kind of relates to it. So here is the answer that I gave. I said for a 1 degree increase in the temperature in Fahrenheit, so that's for a 1 unit increase in X, the number of coffees sold in a day, that would be our Y variable, is predicted to, and then we're going to say decrease since we had a negative slope, right, by, and then we are going to write the positive version of the slope, 0.569. So every time the temperature goes up by 1 degree, we're going to expect to sell a little bit less coffee, about half a coffee on average, or maybe you'd say for every 2 degrees, we're going to be selling about 1 less coffee. Next, we're asked to predict the number of coffees sold in a day with a high temperature of 37 degrees Fahrenheit. So all you'd have to do is just plug 37 into that formula, and you should get out 24.26. So if the temperature was 37 degrees, we'd expect to sell about 24 or so coffees. If the actual number of coffees sold on this date is 27, find and interpret the residual. Well, remember, the residual can be found by taking the actual value and subtracting the predicted value. Well, you should be able to do that based on the numbers from basically number 2 and also the number that is given here. So I'm not going to say any more about that. I'll let you try that out on your own and figure that out on your own. All right, we got one more problem to talk about here, and this is another one for you to try. And I will go over most of the answers here, but I want you to, pause the video and try as much as you can. So here we have some actual data here related to a number of different countries, and we have the GDP per capita in thousands of dollars, as well as the infant mortality per 1,000 live births. Now this one is a little bit trickier because the X variable is in thousands of dollars, meaning that these numbers aren't necessarily just 4.2. This is like $4.2 thousand or $4,200, or this isn't 54.5. This is $54,500, right? To find the actual value, you'd have to multiply each of these by 1,000. Now you don't have to plug these into your calculator by multiplying them by 1,000 first. You can plug them in just like they are, but just keep in mind that when you think about some of these interpretations or maybe plugging some of these numbers in, you're going to have to think about what the number is in terms of thousands, the way that is written right here, okay? So go ahead and plug these numbers into your list 1 and list 2 in your calculator, run the regression like we talked about earlier in the video, and then use some of those interpretations we talked about earlier to answer a couple of these questions, and then I'll be back with you in just a minute to go over some of the answers. All right, so hopefully you've given that a shot. So I'm going to go here and on the calculator and kind of show you the steps that I took to get these answers, and then we'll go over a couple of those answers together. So first of all, you should have gone into your stat list, pressed enter, and typed all those numbers into list 1 and list 2. Once you've done that, you can press stat. You can arrow over to the right to the calculate menu, and then you can go down until you get to option 8, which is linreg a plus bx. Choose that option. You probably shouldn't need to change anything here, just list 1 and list 2. We can go down to calculate, and then we will get kind of all the information that we need. So I'm going to take a screenshot of this so that I have this data. And then I'm going to answer the questions in another Word document here. So here's my Word document. So I'm going to go up here, and I'm going to paste this information in here. I'm going to make this smaller. And we're going to answer each of these questions with the exception of the last one here. So the first question says, find and interpret R and R squared. So I've put in here the general interpretation for R, which is right here. And maybe I'll put out here, this is the value for R, interpretation for R. And the interpretation is there is either a weak, moderate, or strong. And in this case, the value is, maybe I'll write the value first. The value for R is negative 0.6571, rounded to 4 decimal places, typically how many decimals I rounded to. And that is kind of in the moderate-ish range, right? The closer you are to either -1 or 1 is the stronger it is, but negative 0.6571, that's really in the moderate range. So I'm going to get rid of the weak. I'm going to get rid of the weak, and I'm going to get rid of the strong. I'm going to say moderate. There is a moderate, and then this is a negative number, so we're going to use negative. There is a moderate negative correlation between the x variable. Well, our x variable in this case was, let me go back here. The x variable was the GDP per capita in thousands of dollars. So I'm going to say the GDP per capita in thousands of dollars. And the y variable, which was the infant mortality per 1,000 live births. So putting it all together, R equals negative 0.6571, which means there is a moderate negative correlation between the GDP per capita in thousands of dollars and the infant mortality per 1,000 live births. So there's kind of a lot going on there, but basically the higher the GDP per capita, the lower the infant mortality, which kind of makes sense. That's what the negative correlation means. Then we could do R squared. So first of all, we got to put R squared into a percentage. So the value right here is 4.4318. So we'd say 43.18%. of the variation in our y variable. So once again, our y variable is the GDP. Actually, the y variable is the infant mortality one, right? Infant mortality per 1,000 live births can be explained by our x variable, which is the GDP per capita in thousands of dollars. Right? So 43% of the variation in the infant mortality can be explained by GDP per capita. So there must be some other variable out there, or several other variables that can kind of make up the remaining 57%. The least squares line is going to be, let's do that here. It's going to be y hat is equal to the a value, which is 39.87 plus, but we have a negative value, so we can put it as negative 0.7492x if I go to 4 decimals on that one. I kind of want to make that a bullet because it's annoying me. There we go. And then we're asked to interpret the slope. The slope is, of course, the 0.7492. So we'd say for a 1 unit increase in x, but what is x? Well, x is the GDP per capita in thousands of dollars. So a 1 unit increase in that would be a $1,000 increase in the GDP per capita in a country. Since 1 unit represents $1,000, 1 unit would be $1,000. The y variable, which is the infant mortality per 1,000 live births, is predicted to, in this case, we're going to say decrease because it was a negative number, right? We have a negative slope here by the positive version of the slope. In this case, that would be 0.7492. So putting it all together, for a $1,000 increase in the GDP per capita of a country, the infant mortality per 1,000 live births is predicted to decrease by about 3/4 of a person, right? So every time the GDP increases, we are having just a little bit less infant mortality per 1,000 live births. The last one asks us to make a prediction for a country that has 63,500 GDP per capita. So remember, if you're going to be plugging this into this equation here, this is based on thousands, right? So you're not going to be plugging in 63,500 into the equation. You're going to be plugging in how many thousands this is. So I'll let you think about that. And then when they ask you if we should rely on the prediction, there's a couple of things you could consider. One, are we interpolating or extrapolating? And secondly, does the answer that you get make any sense? So I will let you try that one out on your own. So I think that is everything I have here to talk about related to linear regression. Hopefully you found it helpful, and I will see you in the next video.